Hello everyone. In this assignment, we are going to discuss about proximal policy optimization. So we'll implement an algorithm called proximal policy optimization. It is a policy gradient method with the better stability and performance. It limits updates to the policy network by maintaining the ratio of a new policy which is added to the old policy, ensuring that the smoother updates and preventing in drastic changes. The algorithm is also robust to hyperparameter initialization, making it a suitable choice for various reinforcement learning tasks. We'll apply the PPO algorithm to train an agent to play the classic Atari game Pong. So first we'll familiarize ourselves with actions, observation, reward of Pong environment. And this is an untrained agent playing Pong. So first, we'll install the two packages which are named Gym, Gymnasium Atari and Gymnasium Accept ROM license in a Python environment using the pet package manner. So the first package, Gymnasium Atari 0.27.1, it installs the Atari environment for OpenAI Gym. These are a set of classic arcade games such as Pong and Space Invaders, which are often used as benchmarks for reinforcement learning algorithms. The number 0.271, it specifies the version of the package to install. And the second package, Gymnasium Accept ROM license, it installs additional Atari ROMs that are not included in the default installation. These ROMs are not open source and it requires the user to accept a license agreement before use. The quiet flag, it is used to suppress the output of the installation process. And in this code block, we'll import several Python packages for deep reinforcement learning and sets the device to be used for training. The NumPys and Pandas, commonly used packages for numerical computation and data manipulation. And MATLAB is a popular visualization library. And torch.inn, functional, and torch.optim. These are all packages for implementing and training neural networks using PyTorch, a popular deep learning framework. And Gym, we already familiar with that. It's an OpenAI Gym library which provides a collection of environments for testing and developing RL algorithms. And PQDM, it's a package for adding progress bars to Python code. And warnings, it's a built-in Python like module for handling warners. And so finally, the code will set the device for training to be either in the CPU or GPU, depending upon which one is available. And the selected device is then printed to the console. Here, the selected device is CUDA. And the code downloads and imports two Python files, that is PPO Pong utils.py and parallel environment.py, which are used for training a PPO agent to play Pong in OpenAI Gym. The wget command is used to download the file from a GitHub repository, and the #q flag is used to suppress the output of the download process. The parallel env.py, it's a file containing a class definition for creating multiple parallel environments, for which allows in the faster training of the agent. And the Pong util.py, it functions for processing game frames and collecting trajectories. The code then creates an instance of Pong environment from the Atari learning environment using OpenAI Gym. The gym.make function creates an instance of the Pong environment. The ALE Pong v5 argument specifies the name of the environment to create. And render mode, that is RGB array, it specifies that the environment should render its frames as RGB arrays which will allow us to visualize the game. And the print statements will output the following information about the environment, that is actions, states, and available uh, um, states, actions, and available actions. And so in order to reduce the computation, we need to process each frame and to smaller dimension and convert it from RGB to grayscale and remove the background colors. And so the code then tests pre-process a single function from the Pong util.py, which will use it to pre-process a single frame for the Pong game. The env.reset function resets the environment to its initial state, and the for loop advances the game by 20 frames using the env.step function, which moves agents paddle down. The frame variable stores the last frame of the game, and the print statements will output the shape of the original and processed frames. The process single function, it takes a single RGB frame as input, and then it converts to grayscale, resizing it to smaller shape and normalizes the pixel values. The processed frame variable stores the pre-processed frame, and the PLT subplots function, it will create a figure with two subplots. That is, the IM show function displays original and processed frames in the subplots, and the AX dot set title, it functions set the title for the subplot. As you can see, this is the output we got. That is the shape of a frame before processing and after processing, and the text and the graph here. Yeah. And in this code block, we'll define a neural network model. By using PyTorch, the policy model will be used as a policy function for the PPO agent. The init model class is subclass to define the policy model, and the init method initializes the layers of the network, and the forward method defines forward pass neural network. And so the output of the self.fc2, it's the layer has a single dimension because the policy model only needs to output the probability of taking a single action, either left or right, into the Pong game. Now the code sets the hyperparameters for the PPO agent, including the learning rate for the optimization and the values for the right and left actions in the Pong game. The learning rate here is set to 1 e minus 4, and the right and left, the variables are set 4 and 5 respectively. The policy model is created and then moved to selected device using the to method. The Adam optimizer is used to optimize the parameters of the policy model with the learning agent of learning rate. Here we can see the breakdown of the equations. And we have the exercise 1. Here we need to perform the following task, that is add a line to calculate the ratio of new and old, and add line to clip the ratio. So the clipped surrogate loss function takes in the current policy network, the probabilities from the old policy, a list of states in the trajectory, and list of actions in the trajectory, a list of rewards in the and a discount factor, a clipping hyperparameter, and a coefficient for entropy regularization. It then performs the following step. First, it will calculate the discounted rewards and then convert it into future rewards. It normalizes future rewards, and then the third step, it converts the actions, old probabilities, and rewards to PyTorch tensors. It converts the states to policy using the given policy, and it calibrates the ratio between new probabilities and old probabilities. The clipping the ratio to be withheld between the desired range, that is 1 minus epsilon and 1 plus epsilon, and it calculates the clip surrogate loss using the element wise minimum. Compute the entropy regularization term to encourage exploration. It returns the mean of the clipped surrogate surrogate loss plus entropy form weighted by the beta. Now the hyperparameters are defined as follows. Episode, that is the number of episodes which are needed to train the agent, and the discount rate for the future rewards, and the epsilon for the target loss, and the beta, that's a coefficient for entropy regularization. T max, the maximum number of steps for each episode for collecting the trajectories before updating the policy. And the SGD epoch, it's a number of epochs for each policy update, which is the number of times the whole data set will be passed through the policy network during the update. And here we have the exercise 2, we need to perform the following task, that is setting the optimizer gradients to 0 and then back propagate the loss. We have to train it for 250 episodes. um, So the code is implementing a PPO algorithm to train an agent to play the Atari game Pong. The parallel ENV function is used to initialize a set of multiple parallel environments, which allows for efficient training by collecting trajectories simultaneously across multiple instances of the environment. And the clipped surrogate loss function is used to calculate the loss for the PPO algorithm, which involves computing the ratio of probabilities for the current and previous policies, and the clipping the ratio to a specified range, and then taking the minimum between the clipped and unclipped ratios multiplied by the rewards. And the code then performs multiple passes through the collector trajectories using stochastic gradient descent to update the policy parameters in the direction that maximizes the expected reward. Finally, the code keeps track of the average reward across all parallel environments at each episode and displays progress at every 50 iterations. This is the output we have got. And yeah, now we'll plot the mean rewards. So we'll convert the list of rewards to a um, panda series using reward series equal to pd dot series mean reward, and then we'll plot the moving average here by setting the x label and y label and the legend ax dot legend. So this is the uh, plot we have got reward and moving average, and we have the number of episodes and the reward. So as the number of episodes increases, the rewards are also increases, and the moving average is also increasing. Yeah, and the code now installs the necessary packages for visualizing the trained policy network in action. First, it installs the image IO package, which provides functionality for reading and writing video files with FFMG, MPEG as the backend. And next, it will install the PY virtual display package. The code then generates a video of an agent playing an Atari Pong using the trained policy. First, it setups a virtual display to enable rendering the game in a headless environment. Then it creates an instance of the Pong environment with RGB array render mode. And it starts a rollout for 3000 steps where it, it inputs the last 2 frames to the policy. And finally, it creates a video file from the saved frames and displays the video file using an HTML tag. As you can see, this is the video after getting trained. Yeah. So the trained agent, it won 5 games. And so how can we improve this policy? There are few things to keep in mind, like adjusting hyperparameters such as learning rate, discount rate, and entropy coefficient, and clipping parameters, and trying different architectures for the neural network policy, and also increase the number of episodes per training to see if the policy can continue to improve with more experience, experimenting with different pre-processing techniques to better extract useful information um, from the game state. And so a longer training period can also help the agent to learn a more optimal policy. Thank you.